Yes.
Or you can just do it from here.
Yes, we have officially started. Yeah.
You just copy it or leave it?
Okay, so hello everyone. We will now start the session on upper ontologies and standards for material science. And our first speaker will be Gerhard Golbeck from Golbeck Consultancy. Gerhard is a partner in OntoCommons. He's been leading a lot of the activities in the European Materials Modeling Council. He is also one of the main authors of the EMO ontology. And please welcome Gerhard.
Thank you. Thank you. So I hope you can hear me. How are we going to do the? I'm not versed here with the technology on this side because we don't see the presentation on the screen yet. I assume that for the online, I will share the screen here.
So yeah, partager l'audio and then share. You have to select this.
You have the screen, so did you plug the laptop? Yeah, okay.
Yes, and then we can. I don't know if there is this one or just duplicate input.
Okay.
So just can test something to check if people receive the audio and yes. So please ask. Can you hear us online? So please put in the chat, and if you also have a screen.
Yes, we can hear you and we can see the screen. Thank you.
And timing. Okay, I think we're in business. Hopefully, I will do the duplication here, so that online also it's full version. Both, yeah. Okay. So in this session about material science, we're talking about upper ontology and standards for material science. I'm going to introduce more, let's say, the type of requirements. You know, what would we like to achieve? What do we need from the field of material science perspective for upper ontologies to do? There will be a presentation after mine given by Emanuele Ghidini, who will, provide an upper ontology framework that can address these as an example. Of course, as we know in OntoCommons, we work with a pluralistic view, different top-level ontologies. So, but that's what we would like to achieve, at least in this session, to have a discussion around, what do we need? How can we address that? So a number of projects are involved, of course, from the materials perspective that contribute to the development here. These are not just the OntoCommons project, but we heard also yesterday a presentation from one of my colleagues in Nanomi Commons. There's Ontotrans, Open Model, SimDome, Marketplace, VimDome. So there's quite a few projects that have an interest in that. In terms of the requirements for materials, process, and product, what industry requires is, of course, faster development and innovation cycles, and digitalization has been mentioned many times also in this meeting as a driver of that. What does that actually mean? A key part of it is a unified way of representing materials, processing, and the according devices, which then can support the deeper understanding and precise manipulation of the respective influences. That requires a rich materials knowledge capture as well as data interoperability. And of course, what we aim for is ontologies to play an enabling role in the transition from pure description to innovation, to recommendations, to new discoveries, and so on. The challenge in the status quo is that the whole materials and product development is a very big field with many multiple subdomains, multiple information and data resources. Each domain has its own language and ways of handling data, and there's really no common representation system. So we need to organize the data by something that unites the communities. Yeah. So what is that? So we can, of course, there we are fortunate in a way we're all scientists, so we can draw on the material science foundational principles. But at the same time, we need to recognize the different fields, and the fields have a plurality of perspectives. And we will see some examples of that later on as well. We would also like to emphasize the descriptive nature of ontologies. So of course, it's not just a different way of setting up a database. We want to capture the material science knowledge, and we want to project existing and new knowledge onto data. So it's not something that we say, okay, let's have a look at the data and then sort of extract a model to represent the data. We already have knowledge in material science. So how can we use that knowledge and bring it into the ontology? So in that sense, it's a bit what was also mentioned yesterday. Ontology is about the world as it is, but here the world as it is from the perspective of a scientific methodology. We leave the data processing and mathematics to separate implementations. So these talks are not about that. Of course, they are important, and it's just not in the scope right now. So upper ontology requirements, a science point of view. So what is the scientific view of the world? Well, there are core scientific principles. There is an agreement that there is such a thing as the universe, and there are basic rules that apply everywhere. So these then are formalized in natural laws. There are patterns and behaviors driven by these rules that can be uncovered by observation. So observation is a key part of the scientific method. But there's also subjectivity of observation, because observation leads to understanding, but not to absolute truths. There can be laws, but that's different to, that's the current state of knowledge. Similar investigations can lead to different results and also have different interpretations. So there are multiple ways of multiple theories, as we know, and many discussions about that. So there are widely accepted scientific laws built on these, so where a common understanding has been achieved today, and these need to be taken into account. In particular, that there are elementary entities and that they have certain types of interactions. So without going into the details, there is the standard model. That there are things such as, cause and effect, and there are, going back from Newton's third law, and there's conservation of quantities and so on that are related to that. And there is matter with the rest mass, fermions and fields, bosons. They are fundamental families of physical entities. So somehow we have to capture that. Yeah, some of these are from an educational teacher resources side, on the scientific view of the world. So it really goes all the way down to schools. But in the end, there are perspectives on the truth. So this is what we also have to always, these different interpretations we have to keep in mind. So what are the core physical sciences desiderata? What we'd like to do and achieve here? We need to put observations in the center. Very important to capture and communicate observations. So observations are kind of data. They are not yet the meaning, right? So we see something, but then we interpret it. There are kind of contrasts, images, things that we observe and capture in that way. There are physical entities, and we need a clear representation both of the fermions and the bosons, both of the matter and the fields. There are clear and scientifically informed understanding, or there should be a scientifically informed understanding of space-time. So what is space-time? And how do we represent that? Hierarchical connections are in part, now we're getting more into what we already know through observations, that there is something like a hierarchical nature, or going back, way back, but today, obviously, with the atoms and so on, atomic nature and hierarchical nature is very important, and that multi-scale nature needs to be captured. We need to connect physical entities to models. So the scientific worldview before is like we apply imagination and make models in our minds, but also formulate them in theory. So there's a model about things. We make careful choices about what is known absolutely. So most of these things are kind of observational and relative. Absolutely, pretty much only the universe, and there are these quantum elementary entities and so on. But we also have to, at the same time, deal with them. So not just Newtonian physics, but really quantum systems, which also means being careful with space-time, as we know from a scientific point of view. So at the upper level, we want to represent matter and material, including their structure. So a meaningful conceptualization according to physics, classical quantum mechanics, chemistry, and material science. And a representation of the characteristics of materials. We need to capture multiple ways here in which a quantity can be determined, including experiment and modeling. So we have a multiplicity of observations and measurements. So what are properties of materials? How do we arrive at that characteristic? And so these foundations for material are then foundations for material taxonomies at the middle and domain level that should be able to build firmly on this upper ontology. They should inherit a foundational, fundamental meaning from the upper level. This is what we need to provide now to the people developing also domain ontologies. The requirements provide a meaning to the connection of observations and materials properties at a fundamental level. So again, the question, what is a property? And they ensure a meaningful multi-scale representation of matter. And again, coming back to there are no absolute truths and so on. So we still then, when it comes to domains, as we heard many times in different scenarios also, we have to deal with cross-domain conceptualizations and concepts, for example, from different existing standards that may be difficult to reconcile with each other and top-level ontologies. So here we kind of hit reality of existing conceptualizations. So I actually, that obviously needs to be noted. So it's also a session about upper ontologies and standards, and I mentioned properties as an example. So okay, let's look at standards. I've just selected here one, which is the ISO 10303 part 45, and then also part 235, which is material and other engineering properties. Well, it's now used mainly for product, but it was designed originally also to capture materials. In there, the meaning and semantics of a property is defined by the particular process required for its measurement. So a property is not something that is somehow given by the material. No, you have to apply the scientific method, and you can only say it's a property of that material following that process according to the standard. It may describe the behavior of a product or a process. So it cannot be independent. It is related to the process of its measurement and to the object that it describes. So it has a triad of relations here between the observation, the measurement, the object. So property, measurement, object relating to each other. So there's some references here from, including Norman Swindells, who is also involved in this work. And we have had interactions with, has written a lot about that. So, so I've adopted this. So usually you would say product history. So just to make it kind of more materials, I've replaced product by material because the standard is supposed to be both for product and material. So we then see this 4 steps. So the material, then the observation process, then representing, how do we represent it in a type of property representation with a system of units, and then we get the data, the property values, which we then say they are then the property of the material. So that is what a property of a material looks like. Of course, with all of the additional data and descriptions around it, such as the process properties, the resources, and so on, which are, of course, important then to define an industry standard. Other one relating to that is nanotechnologies. There's separate standards on that. So talking about the nanoscale property, so this comes now from a different community. Basically, it says, well, a nano object can have a property which is related to its size. Kind of an interesting one, because maybe that standard should also go back to this standard, which says material dimensions here. So it's, or one could say this could be unified because the dimension of the material is already part of that standard. So it kind of, this follows from that. So an interesting exercise maybe to look at alignment here. Now coming down the scale, as it were, and looking at some challenges of different communities and how these different domains and subdomains look at things and how we deal with that. So pluralism challenges. So the IUPAC Gold Book is the Bible of chemical terms and definitions. It's a fantastic resource for also the ontology development, which are also ongoing in that field related to that. So there's a chemistry definition of atom and molecule. So we have a nucleus of positive charge Z and Z electrons. And then the molecule is an electrical neutral entity consisting of more than one atom. So we have, this is the atom, then this is the molecule. But then also we can talk about a molecule from the chemical physics definition is a neutral entity consisting of nuclei and electrons, no more atoms. So we have different types of taxonomies here, and we need to somehow reconcile and from an ontological perspective these two different approaches. So just a few things at the end of the talk that already go a little bit more in what the Commons work is doing. So how can we represent fundamental material science concepts in upper ontologies? So at the mid-level we have, for example, physical matter, atom, field, quantity that I mentioned. How can they be mapped? So the goal is to establish a transparent and properly explained connections between these ontologies and golden standards actually acknowledged from domain experts. So some sort of mapping that provides a detailed and informal elucidation of the ontology entity in natural language. So a concept vocabulary for materials ontologies is needed and will help the work. And this approach will be also further explained on the training day on day 4. So if you take the atom, so I can't read now in the time all through that, you can then explain the details about what the atom is, and then you can look at, okay, tentatively, so how can you then align this with the different ontologies? So here we have the work on the reference ontology from a logic perspective. We already have some connections, and then we can see how the atom is represented in MO as a molecular entity, matter physicalistic, or a material entity in BFO, or a physical object, a non-gentive physical object in Dolce. When I look at the physical field, a region of space-time in which each point has a physical quantity associated with it, we see, however, that some of the ontologies that do not deal, naturally, let's say, with matter that doesn't have a rest mass. In BFO, we then have an immaterial entity as a field, whereas in MO, which was a sort of a science ontology, is obviously still a physicalistic thing, which is defined. In Dolce, it is a feature of a physical endurance, but which actually, depends on other physical quantities, entities. So it, has actually some very nice characteristics of the field. So one can then start to look at, how do the current ontologies address, and this is a question now for the discussion. We're not answering that here, and which is ongoing, but also hopefully helps the field move forward in terms of, okay, can we satisfy all these requirements? How can we deal with them? Are there maybe even any changes required, and so on, to deal with these types of requirements? So in the end, the users should expect the ontologies at that level to facilitate the translation of material representation, a rigorous setup of user cases from a material science perspective, gathering of data, and obviously then to predict behavior, but also at the classical and quantum mechanics level measurements. So we need to, in the field, embrace the scientific foundations for material science knowledge representation, so that these key concepts and standards are represented as naturally as possible, embracing multiple views of the world, and facilitate what I would call material science intelligence. So put it in there right from the top. Thank you very much for your attention. And thank you for the co-authors, Emanuele Guidini, and also Francesco here, who's in the audience, so I should mention them.
Time for questions.
Yeah.
Okay, so now time for questions.
So I have 2 questions. One on I do not know exactly what has been done, so it may be, of course, disconnected to what you have presented. The first one is in KBI. There is a description of atom, of a
Yes.
quantum, and so on.
Yes.
What you suggest, does it give information, or is it in agreement with what you are suggesting, or are there some discrepancies?
Yeah.
So that's my first question. On the second, that is more practical. When you have a material as usage, you very often have what we call performance. which is a subset of property. Have you thought to this approach, which is more user-oriented?
Okay, thank you. So the first question was about the KEBI ontology, right? So, I mean, one of the fields where we're working with the bridge concepts is to say, okay, because KEBI is basically, roughly speaking, I think it's a BFO based ontology, is how we can then use that, and it's already being shown relative to the system here, so that we can do the alignment reuse by building these types of maps, right? So that's one aspect. The other aspect is there are, if we then pose these types of questions that I said before, for example, from the IUPAC Gold Book, if you go down to how is a molecule represented really, and there are different ways of molecule representation, you do uncover that you know, there are certain ways that are not captured in KEBI, also like fields are not captured and so on. So okay, this is more a question that then can go back to the community. It depends on the use case, of course. You know, that I think it's important to keep in mind that KEBI was also done for a particular use case, and now sometimes it's used. Okay, this is like this is the chemistry ontology we have. We just put it in. Yeah. So here let's go back and see, you know, what are the things that you need to answer, and then how you best do it, how you extend also then that system. Then for the performance, well, you know, in the application cases, which are part of the different projects that I show, these are about materials developments for performance, for example, in like steel production and so on. So in the end, yeah, I mean, performance is another way of, you know, expressing an observation against your expectations and measurements of testing and so on. So in some ways we would treat it in the same type of framework. But the point is that, can you connect the engineering performance in the end, as we come from material science, to the really more scientific description of the material, yeah, the chemistry and so on, because in the end, this is maybe a more bigger overarching thing to get to this materials attention, to get a deeper knowledge of materials in product development and performance.
Very often, the performance cannot be clearly described just by a scientific property. It has some other description criteria that are not really accessible or not precisely
At the same time, we are also working. I mean, this is also kind of ongoing work on by another colleague of in Bologna, and in particular on, for example, how you describe, for example, verification and validation. So I'm just saying, because validation often relates to performance criteria, right? I mean, so you have certain, there you cannot, as you said, specifically say, you know, it has to have this type of material science about it. It is relative to an expectation of performance of a product, and how can you capture that as part of our representation. So bringing in a very, I mean, we're working on, for example, integrating all of the different ISO standard representations of validation and so on into that framework, so that these types of questions can be, at least you have the underlying ontological framework to address them.
Thank you.
Oh, yeah, the microphone is just here, so.
I have two-part question. The first one is about space and time. How do you deal with the different location, for example, in space and time? And the second one, How do you treat different definition, for example, of molecule, as have you shown, as it is chemically and physically defined? So there is like two different definitions,
Yes.
and how do you treat this?
Yeah.
in each way?
So can I leave the I mean, there's obviously different way. I mean, I'm just talking about in general, right? So now I would have to talk about, okay, how do we, I mean, in that sense, I would then talk about ontology. And this will be also addressed in the next talk. So how space and time is actually addressed there. I mean, the other point is that I mean, there is no way around it other than including the different ways of representing entities like that. I mean, especially when it comes to also quantum systems, you have to leave these different options open. They are then maybe in the instantiation addressed of what do you want to have in a particular application. So so it's all about in a way dealing with systems or enabling the ontologies to be built to allow multiple different representations. But then you have to agree at what level. For example, in the end, are you talking about molecules, or are you talking? And you cannot reconcile necessarily the same system that talks about quantum side of things. But more will be addressed in the next talk about how we deal with some of these things. So.
Thank you. I don't know if this is audible enough. I'm trying to be at a higher point. Do you want me to come in the front, or?
Maybe.
I don't know. Can you hear it online?
I'll come in the front. It's easier.
It's about online people.
Yeah, I realize that bit.
Maybe they haven't heard anything.
Yeah, we can hear and see you. Good.
All right, great. So I think you did touch a huge problem, something which I would say, okay, by experience and knowledge, we as humans have gained, at least from the materials perspective, for what, 15 years being in different schools, trying to understand how this works, and I still don't guarantee that I understand perfectly everything. Now, saying that, you spoke about the cause and effect, and I think there was a question where you said about performance. My take on things and the way I see it is, at the end of the day, I've got a product, an asset. I need to make sure, assuming this is a complex asset, I need to look at the remaining useful life aspect of it. I need to control or understand when failure could actually occur and can I prevent it? And that's where the whole of the reasoning of the asset management comes in place. You did briefly mention about the cause and effect. I know it's at a higher level. Have you looked at integrating the process level information? Because it's the operational perspective and how a material behaves in certain conditions is what the material information comes through. Are you looking at the practicality of what may be required in the future? Again, there is things like advanced materials coming in place, you see. So how good are we in making sure that our database is up to date on one end, and how is it translated through the ontological perspective?
Yeah, I mean, this is
a complex question.
Goes
sorry about that.
In a way, far beyond. Again, I would say, core to. I mean, we will see that more in a minute in the next presentation as well. Sorry to refer to that a few times. But what I said here about the, if you just take the philosophical basis, let's say, of this ISO 10303 in my view, and we use this, what we call it, semiotics. So basically you should refrain from saying that there is, a material has this property. Yeah. Because it depends on so many things, right? How has it been processed? What is, there are many steps. So you have to have a system, first of all, in place that captures, that puts meaning to these numbers, right? And this is, in the end, in my view, the core to, or the key to addressing also the questions that you raised. How you do this in practice, I mean, it's clear that you need to have this richness of information, and you need the ontology as a system that gives you a good framework of how to do that. I'm not saying that this will be practically still an easy thing to do, but this is
No, because what you said is right. The practicality. See, if you ask me as a supplier, a material supplier, would I actually vouch for the accuracy of the data? Because at the end of the day, that accuracy levels will impact on the degrees of freedom such a material is being subjected to. So the ability to capture that level of information is going to be extremely hard. Probably there is also this data protection, probably levels of consumer information which can be commercialized, and so they don't want to have that because it's a commercial entity.
Oh, of course, this is another thing. Of course, all of that information is locked away. Yeah, I mean, and currently verbally communicated. So basically, you can go to match. You can say on the web, what gift I need to do for this applications. I need these materials according to these properties. Gives you the materials. Do you know how they make business? Is because there are a million other questions people have when they want to use the material, so they have to ring them up. Basically, they have to have a special contract with them and pay for that information to be provided. So
no, it is because I work in tandem with the Grant Material Pack. So they are we're trying that repository for material properties. You can go and refer to as a guidance. Again, we can't course go to the T. I think it's an interesting challenge because that relationship and the transfer of that knowledge between those two aspects, in my perspective, I struggle, and that's one of the reasons why it's directly a complex problem. So probably we don't know where we go as a community. You should be aware. Thank you.
Thank you very much. So we need to go now to.
Now we should move to the next speaker. Okay, so now I will give the stage to Emanuele Gadini, professor in the University of Bologna and the main developer of the EMO ontology. And Emanuele, I hope you are ready and you can hear us. You can start the presentation.
I can hear you.
We can also hear you. So
why is not working now? Okay.
Can you zoom in?
Okay. Can you see my screen?
Maybe I have to. Yes. Let me see how I can.
Can you see my screen?
We can see your screen. I now just need to try to understand.
Can you hear me?
Yes, we can hear you.
Okay.
Full screen.
Why is no, I'm here. Okay. Okay, please, you can start, Emanuele. Now everything is ready. Decided.
Thanks. In this presentation, I will try to show how we implemented some of the needs presented by Gerhard developing the EMMO ontology. So first of all, the EMMO ontology started by practitioners in material science in 2018. There is not a fixed date for its start, but I think this year is representative. And under the governance of the EMMC, and it is elementary since it is based on fundamental scientific concepts. You these multi-perspectives because it's able to describe the world in more than one way, and it is based on three different primitive concepts that are causality, mereology, and semiotics. So let's have a look at how the MMO very top level appear. The idea behind the MMO is that the world should be represented as a causal network of quantum entities being of the types and the interaction being of the types prescribed by the standard model of particle. As you can see, the taxonomy of the very first level of the MMO is based on how these mereological atomistic entities that we call the quantum are connected together. And also here you can see a very, very general definition of a system that, in this case, a causal system that happens when you have several chain of entities that are related together. So it's a definition that captures the actual etymology of the work system, in which that means things that stay together. Also, the top level of the relation of the MMO, in this case for the causal primitive relation branch, is shown here. This is actually only one a part of the actual relation that we developed in first order logic due to the limitation of our DL. And as you can see, it is based on the concept of causality and distinguish between causality that happens directly, so with a sort of a spatial temporal contact, or with a distant causality. And these relations are specialized in relation that capture the spatial relation and the temporal relation. Another important characteristic of this causal relation is that they are also create also a hierarchy of causality that navigate through mereology. For example, if two macro objects represented by these white boxes are in cause relation, then it is implied that there is a lower level mereological part that is in cause. So this concept, this methodology to represent causality, this property of causality, is what enables us to express causality at a very high level, and then, if we want, go to a very lower level. So in this sense, the MMO can be considered a 4D ontology, even if there are entities that are outside space and time, like the quantum, because it is strongly connected to the becoming of entity from something to something else. So in order to be, I would say, the more ontologically possible, so to be objective as much as possible, we decided to design the MMO to be able to capture what physicists consider to be, the state of things, the state of affair of reality. So, which is the standard model theory that is based on quantum field theory. So our idea was to create something that could represent the fundamental interaction, like the one that you can see here, the scattering, the quantum scattering, the Bremse-Strahlung effect, the pair production, and so on. And here you can see an example of representation of Bremse-Strahlung, for example, in the MMO, in which spatial and temporal relation connect together the different particles expressed as mereological entities, so that this type of pattern of picture constitute the most fundamental process that the MMO can represent, and this should be part of it can be part of macro description of the things. So this is what we consider to be the something that so these processes are what we consider to be something that everybody should agree upon. So that is what we consider the objective foundation of the MMO. But there is no need to a particle physics degree to use the MMO, because if we can go up to that level, it's not necessarily to for the user to go to Feynman diagram level or to standard model particle level, because if due to the properties of causality, you can simply, for example, say that these two atoms have a physical connection through a photon exchange, for example. So which is usually what happens when you do molecular dynamics simulation, in which there is an interatomic potential between two atoms. So you can describe the things like that, or you can, for example, be more detailed. So by going down mereologically, expressing the fact that it's not the actual overall atom to have this relation, but it's actually the two electrons of these two atoms, and so on. And then you can go further and further if you want. So the idea is to provide a framework that can enable the user to describe the phenomena occurring at macro level, but at the same time have an axiomatic system that guides you if you want to dig more and more into the details of material interaction, and gives a representation of materials that then a physicist, a chemist, or whatever can use and then apply to its models. Then there is also mereology that is part of the MMO. Mereology is a second primitive relation used by the MMO. As you can see, it's quite standard in the first part, and it is based on the atomistic general extensional mereology, which is a quite well-known theory. But then it is specialized in relation that make temporal and spatial part arise in as a subclasses of as subrelation, as subrelation of the proper partud relation. So now we can also use partud to represent parts that are temporal or spatial or have more complex relation with the rest of the whole. So this meritopology emerging from the MMO is the meritopology that it is based on physics-based causality. So why we need so fundamental level of detail in the description of material? Because we want to speak the language of material scientists, physics, chemistry, to enable an ambiguous representation of all entities, ready to be translated into one of the existing physical mathematical models. So our idea is that I represent you the material, the world entity, that you, chemist, you can use your mathematical approach, or you physicist, you can use your own mathematical or physical mathematical approach to describe the things, and so on. So that's the idea. This also enables multiscale representation of world entities and provide a strong foundation for material-based taxonomies. So I can create a taxonomy in which the granularity levels are connected with the required interaction between the constituents. But the MMO is not only for materials. Our ambition is to provide a way to look at the world using the eyes and categories of applied scientists, and in general, more in general, with people who manipulate things, such as engineers, physicists, chemists, modelers, material scientists, technicians, construction builders, and so on. So that's the idea. But beware, because we are applied scientists. We put our faith on material entities. So in this ontology, only material entities exist. I would say not material. That's wrong. I made a mistake. Only physical entities exist, because a photon is not a material. So that's wrong. Sorry. And abstract concepts are represented by classes in the MMO using a nominalistic approach, and the individuals only refers to material entities. So this is a sort of radical materialism or physicism, but this forces EMMO users to be accurate in the declaration, avoiding ambiguities that are typical for abstract concepts. So, for example, there is no abstract concepts object standing for the information content of this presentation. The only archetype for this for the information delivered by this presentation is can be referred as the presentation that I have on my laptop that has been duplicated or modified by somebody else. So that's the idea behind this nominalism. So this is an example, a fun example of the concept of love is not an individual in the MMO. It is simply the collection of all the object, for example, someone who is imperfect, but it is perfect for you, or a process, so so the process of sharing everything. So these two individuals, object and process, are instances of love, which is not an individual, but it is a class that comprises things that comes from other part of the taxonomy. So the MMO tries to capture the world using perspectives. So the mere causality part is simply what we know for sure about the world, what everybody agrees upon as applied scientists. So the perspectives are, as you can see here, there are some perspectives. Each perspective provides a covering action for all the causal objects according to a specific categorization. So everything in the world can be separated in fundamental classes for the data perspective or for the reductionistic perspective and so on. So these perspectives are naturally built in order to be used at the same time. So for example, something can be of a type of data that at the same time can be a physical entity. For example, a CD-ROM or a DVD, it's an expression of for data, and the physicalist provides information about how these data are materially structured. And these are the perspectives that we developed up to now. There is not a fixed number of perspectives, but these are the ones that we consider to be the most useful for our applications. So, for example, the holistic perspective is a perspective in which we formalize the relation between the whole and the parts. So we require what type of part are needed in order for a whole to be what it is, and at the same time to define the role according to the whole to which the entity is part of. So this is a way to express the relation between whole and parts based on types. Another perspective is the physicalistic perspective, in which everything is seen as a matter of field. So and this perspective is the one in which we can place most of the material taxonomy, because you look at you can look at a person and you can see it as my friend. But if you look at this person as a physicalistic, you see this person as an aggregate of molecules, for example. So this is how the physicalistic perspective works. So I look at things simply as an aggregate of matters and fields. And the reductionistic branch is another perspective that that is devoted to the creation of hierarchies of granularity. So the idea is to be able, using this approach, to create rigid granularities, and that creates a direct rooted tree, so that it is possible to define the properties of the upper granularities using the properties of the lower level granularities component. So that's the idea behind the reductionistic. It is very useful because it is based on predefined tessellation of entities. So you can prescribe exactly what type and exactly in which configuration, in which topological configuration each granularity level appears. So for example, you can declare that a molecule is made of nuclei and electrons, for example. And more than one granularity hierarchy is possible to be developed in parallel, so without the problem of being incompatible. So you can have more than one hierarchy descent coexistent. So reduction is used in the MMO because when a material scientist look at things, it looks at something like that. So it goes from the macro entity to the constituent, and maybe it needs only to stop here, but maybe another branch of your institution or your company is devoted to calculate the properties of this component, starting from the microstructure. So it is probably it is good to have the possibility for someone to have this the possibility to stop here, or if you want to use modeling to retrieve the properties of the component. So This is another example of the ambition of the MMO that wants to go from the quantum level to the macro level, covering some entities that you can usually find in material taxonomy. This is another example of a multigranularity. You can see in vertical you have different granularity levels. We can start with the elementary, the nucleon, the nucleus, and then the atom that has direct parts, nucleus and electron. And then we can define atom-based mesoscopic object that has direct part atoms, molecule-based object that has direct part molecules that has part covalent bonded atoms, or atom-molecule composite that has direct part molecule or direct part atom, and so on. So this is an example of granularity hierarchy that can be prescribed by the MMO. And also it is possible to create cross granularity classes based on the properties. For example, a nanostructure is an entity that has one dimension between 1 or 100 nanometer, for example. So it is also possible to create cross granularity classes that capture the properties, that categorize things in terms of properties, and they fit very well with the multigranular description. So this is an example of application of the MMO to the description of material. A very important part of the MMO is the semiotics. So this is used to connect so the physical quantities, for example, or the opinion of someone to some entity, or the key performance indicator, or whatever, to entities. So the idea is that we want to document, keep track in the MMO about the object that is the subject of our observation. We want to keep track of the process that generated the sign that stands for this object. For example, the thermal conductivity is a sign that stands for a particular object, and it is measured by an experimentalist through a particular process that, for example, is described in a standard document. So in this way, we can create a semiotic representation of the assignment of properties to objects, so that it will be possible to document and to keep track for what class of people, for example, this property is a property for that particular object, because for some other there may be a disagreement. And that's always the case when you have characterization. So there will never be a measurement in agreement with another. There will be always some discrepancies that maybe can stand within a tolerance, but every measurement is different, and it depends on the process and on the experiment, also of the time of the day which you make this measurement. So the idea is to keep track of this by using this semiotic approach. Another usage of the semiotic process is to connect models. For example, this symbolic representation of a physical process, which is the force exerted on a mass. This is another example of semiotic process. So for some scientists, this is a truthful sign. This is an icon actually for semiosis. Is an icon that stands for the physical process of acceleration, for example. So this is another way in which we use semiosis. So we can combine reductionism and semiosis, for example, here. For example, we have models that applies to electronic, that are called electronics, so that applies to when you look at things in terms of electrons and nuclei. And we can represent entities in the MMO in this multigranular way. And these models can be assigned, can be considered to be assigned for all this scale of entities. Or, for example, we can stop at this granularity, at the atom granularity, and then we can define models that stop here at atomistic level. So these are atomistic models, for example. Or we can stop at this level, and then we can assign mesoscopic models as a sign that stand for entities that goes up to this granularity level, and so on. And then we can also go to continuum. And then we have continuum entities that can be modeled by continuum models. So the MMO combines reductionism and semiosis in order to specify the range of the models according to the granularity, for example. So this is a way in which we can combine reductionism and semiosis. Another important perspective is the data. Data perspective is based on the work on Luciano Floridi on information. And for example, perspective is devoted to characterize data and physical patterns or gradient according to the characteristic independent from the carried meaning. So this is an example of data. So, but how to combine
Well,
data?
I will
Yeah, please.
ask you if you could go a bit faster because the time is already.
Okay.
So we have some time for questions.
Okay. An important aspect of MMO is to separate syntax and semantics. So semiotics is a way in which you provide meaning to data, and then information is defined in the MMO as data that provide a semantic meaning, so they are attached to an object. So the concept of physical property is exactly a data, so respecting some syntax connected to an entity. This is an example of how we represent the data syntactically speaking, and how we can connect this data that the value here as a semiotic sign for the standing for a material, keeping track of the process that originated that value. So we can also, using reductionism, map file format and specify that from specific data set, some part of the data have a semantic meaning. So, for example, temperature, pressure, and so on, according to the topological position of the data within the format. Oh, okay. And the final example is the crystallographic ontology, in which the MMO use this approach in order to represent the crystallographic information file by separating the data that we have, so the value, in representing this value as an expression of a syntax, of a data type, of a semantics, and then using semiosis of the MMO, we can connect this to an actual material entity. So just to mention that using reductionism and causality, we can create also a directly acyclic causal graph that can represent workflow at different granularity level. So for example, we can represent a computational workflow, also keeping track of the data and the data format. And this workflow can be multigranular. So I would say, for example, that if C is the workflow, you can investigate the workflow as made of this task, and you can also represent the fact that B is made of other subtasks, and then you can have the possibility to create a multi-granular representation of workflows. This is the MMO modules, but I will not go into the detail, just to tell you that we have a criteria to divide the ontology in levels that matches the classical separation in top and mid-level ontologies. And that's it. I think that if you are short in time, I think we can skip to the conclusion. And the only thing I would like to mention that was questioned. There was a question in the previous presentation, is how to deal with the possibility to have different definition of for the same concept, for example, molecule. We focus on concept and not on names. So the MMO is using unique identifier, alphanumeric unique identifier, in order to represent concepts. So if you have two different definitions of concept, we will have two different concepts, and then we use the alternative label here in order to say that these two concepts share the same alternative label. And so that it is possible to search for the molecule, and you will end up with two different concepts, and they will be aligned with ontology in different ways. So then you can keep track within the ontology of different way in which two different communities define something that usually goes under the same label. That's it. Yeah, that's it. So I would like to skip to
Thank you so
the
much.
questions.
So I will ask if there are any questions.
Please check online.
Let me see online. So I don't see any questions here. Yes, please, please. So you have a question, Emmanuel.
Thank you, Emmanuel, for the presentation. I have a question about the semiotic level. You have shown, for example, a picture when a person see a cat. There is different levels of how we conceptualize the cat. Yes, but for example, if we see the person sees only the tails of the cat, there is some semiotic process going to figure out if it is a cat or lion or something like that. How do you deal with this, like different propositions or possible interpretations, if I may say, in this level? I'm not sure if I'm clear, but
Okay. Okay. The example that you just suggesting is an example in which the tail is considered to be an index for the cat, for example. So in this case, the entity tail, that it is the thing that the interpreter sees, falls under the category of index. And then what you can declare is that this individual is an index for another class of entities, which are cats. So the class cat. So you don't know exactly which cat is the whole to which the tail part belongs, but you know for sure that this whole will be under the class cat. So it is possible with the MMO to represent this also this process. I don't know if that.
yes. Thank you.
Then we still have 2 minutes for a short question. Otherwise, then we start with the panel discussion. Okay, I also don't see anything online. So thank you so much, Emmanuel, for the presentation. And then we move to the panel discussion. And I think for the panel discussion, only me and Gerard are here. So Arco asked us to sit here in front so everyone can see us. And I just pick my support with some questions. So first of all, I'd like to welcome everyone to the panel discussion. And before starting, I think it will be nice to have maybe a short introduction for everyone. If you could say a line about introducing yourself, it will be nice. And afterwards, we can start with addressing some relevant questions within the material science domain. Okay, so maybe I can start myself. So I'm Joanna. I come from Fraunhofer IWM in Freiburg, Germany. My background is in chemical engineering, but since I joined Fraunhofer in 2019, I've been involved with the materials informatics team, and I've been working in the subject of ontologies development.
Thank you. Well, you introduced me earlier already. So Gerhard Goldbeck from Goldbeck Consulting, and also the EMMC. And my background is in polymer physics, actually. So and in modeling and simulation of materials. And yeah, one of the co-authors of MO as well.
And from the audience, anyone to start? Maybe we see next Emanuele.
Yeah, I'm Emanuele Ghedini from the University of Bologna. I'm a nuclear engineer, so I've been educated to radical multiscale from the very beginning. I've been involved in the EMMC thanks to European projects, and I've started to work on the MMO, and now I am with Gerard and others part of the development team of this ontology.
Next year, at least in our screen, you see Silvana.
Hi, everybody. Thank you, Joanna. I'm Silvana Marcella, the CEO of Trust IT. I'm the communications manager with others on my team for Onto Commons. And I'm on this panel because I also coordinate the Stan ICT project, which is a standardization project supporting European experts, as well as the HS Booster, that also is a new CSA that supports standardization, not just in ICT, which is nice. So this is a good area where also ontologies are playing a high role. And in Stan ICT, we put together a landscape analysis of all ontologies, studying over 140 at the moment. And this report will come out in Q4 2022. Thank you.
Okay, next we have Norman.
Hello, yes, I'm Norman Swindles. I'm responsible for the ISO standards that Gerhard presented so clearly in his presentation. I've been involved with solving the problem of computer representation of material data for 30, 40 years. But I think the kind of issues that Emmanuel raised are becoming more and more important. The standards are representing really macro and engineering concepts, but several of these concepts really rely on what's going on at the atomic level as well. So there needs to be some way to connect the engineering level to the fundamental level. And I'm very interested to see how this probably can be achieved by these kind of developments.
Thank you. And Anne de Baas.
Yeah, hello, my name is Anne de Baas. I have been working with the European Commission for 30 years as a project officer, but retired some 3 years ago. After the ontological quarantine, I've started my own company, and I now have a contract with Gerhard to work on certain EU projects. And for the rest, I work a lot on the EMMC as such. I have been the author of the review of materials modeling, which was the start of the multi-perspective on materials. I think standardization is an important part, so I'm happy to contribute to this panel.
Okay, thank you very much. So then I would say that we can start the discussion, and then I will start with a question. There is a follow-up also from Gerard's presentation. So what are the requirements for a material science ontology, and what does it mean, in fact, to have a top-level ontology for material science? Are these generic concepts like continuant item collection really necessary for such an ontology? Can you comment on that? What does it mean, top ontology for material science?
My question would be, if you have a top-level ontology, that implies there's a lower level ontology. So what does what would the hierarchy look like? There was a related question raised by somebody yesterday to say, should there be a system of ontologies? Should you have different ontologies at different levels in the understanding? This kind of approach we've used in the ISO standards, where we have not so much ontologies but dictionaries, and we can enable the one dictionary definition to reference. A mention of a concept in one dictionary can be referenced to its definition in another dictionary. So you don't need to have a multiple, just to have one dictionary, but you can have a multiple collection of dictionaries with references between them. Would that be possible with your ontologies, to have references between different ontologies?
Yes, yes, it would be. I think Emanuele gave an example, of that, so that you can actually, keep. Really, you have to work on the conceptualization side and agree on the conceptualizations and not get fixed on a name, like molecule and so on. And then you can also work and integrate different dictionaries in that way. If you understand the meaning behind what the experts wanted to express, that's the key. The other thing, I mean, obviously, I already talked about. My presentation was about that topic, but I think the one thing I would highlight from that is that materials ontologies should derive, should be able to use or derive their foundations from that, and what we have just talked about. So they shouldn't deal with or understand the details of merio-causality, but there should be the relevant perspectives and also the relevant object properties that are suitable for the material science application, but they are absolutely founded in the top level. So this is the key thing now as we're going forward also with the MO developments, is to provide this type of material science level, right? So what we are now is the foundation of material science. So make sure it's founded in proper scientific approaches. But that doesn't mean that everyone, as with the example of the Fermi diagrams, has to go back to that. No, not at all, right? But we need to ensure the right connection, but build the tools and also the terminology expressions of when, what, for example, about connectedness, right? That in a particular application field means different things or is expressed in a different way. So this is now a key project going forward.
Thank you.
Could I add to the discussion, if I may, from looking at it from the work that happens within the projects and CSAs? Is that, we've had discussions with Gerhard, Emanuele, and Norman in the past. I mentioned at the beginning that there is a landscape analysis being carried out in STAN ICT, and there are 140 lists of standards. And Norman, you're working on the ISO, etc. And we heard some discussions in the plenary also before on where there's so many existing standards out there. How can we manage to speak to the different standards bodies? And I think this was a sort of a question coming up after that. There's some form of harmonization going on. Do you think that it's not even a question to anybody, but do you think we're ever going to get to that possibility? And how the work we're trying to do in the landscape analysis is really trying to document this so everyone can go to one place and knows what's going on. But do you think this is an effective? Is there something else we can do? Perhaps is a better question.
maybe I would like to bring to you when we started to work with the ISO people in Germany, and they explained to us how standards actually functioned, and they told us that two people can deposit a standard, and then at the ISO body they sit there and wait until people adhere to it. And I think it is this process that is the most important. There are 1,000 standards, but at a certain moment, the world or the field will only adhere to one or two of them. It is like with the English language. Yeah, it's a natural process. People have their own language for a long time. But at a certain moment, everybody realizes that it is maybe better to speak one language and do the English. So for me, it is this in the adoption by the world that will be the most important. Now, but the question is, at this moment, I mean, do you need a TLO to do this? And then I think this TLO is, for me, a mechanism to communicate. You can communicate within the material science world by people having different views and different documentation systems and trying to harmonize this via things that they have in common, which sit in the TLO. But you can also use the TLO to reach outside of the material science to other parts of the world. And then I think it's very handy that you identify the items that are in common and that sit in the TLO, by which you can reach out to others.
Okay, so to facilitate cross-domain interoperability, right?
Yeah. I would also say that I agree. I mean, with what Anne said, and obviously later today there is going to be a presentation on the IDMP project. Which is basically an implementation of an existing standard for pharmaceutical substances using ontologies, and I think it's a good example in terms of how can ontologies be used so that the actual implementation and use of a standard in practical terms by companies and so on becomes alive, and existing questions of interpretation of what does it mean, a substance. And also in that case, I think they also have these cases that there are different agencies that describe or define a substance in different ways. So you can combine standards and other definitions from agencies and so on. So, or in our case, multiple standards, for example, ones I showed with the materials testing, the 10303, and then the nanotech standards. You could build systems where I think ontologies bring the standards to life and bring the standards to applications, addressing competency questions that the real users of these standards need to be answered. So I'm not interested myself in new standards. I'm interested in ontology for bringing that to a new usability level and interoperability level.
And maybe related to that, then how is currently the involvement of the standardization bodies in the community facilitates actually the development of these standards? Because most of the ontologies that we are using, I believe, in our community are not standardized. So how can we make the existing ontologies a standard? And when does it make sense to make some of the ontologies a standard?
I think the problem, to answer Silvana, is in way there's too many standards. The problem with the ISO system is that it's almost designed to create more standards. In other words, you've got a large number of committees, each one justifying their existence by creating standards, and there isn't no lack of standards, but the problem really is, where do you stop? At what point in the communication process that Anne de Bass described, we're getting to the stage where we got a multiplicity of standards, like we have a multiplicity of world languages, and we're starting to run into problems where the same concepts are represented by different people in different ways. So, and don't whether a standard is as endorsed by ISO or similar kind of bodies, it is some way to go. There needs to be some more universal understanding if such a thing could be achieved. And I don't know how that would be achieved, but we have so many standards, but I'm sure that not all of them are implemented in use. In fact, ISO 103 Part 235 has not been adopted in a wider sense. There needs to be another level of understanding which is somehow different from the idea of a standard. I know that sounds rather idealistic, but it seems to me that there needs to be some kind of common understanding approach. And at the moment, I don't think there is such a common understanding approach in the materials domain.
I'm very happy that you say this, because it's really, for me, also the original idea of the Onto Commons. It does not ask for a standard. Yeah? People misinterpret the call texts.
Yeah.
It asks for a standardized documentation system. Yeah? And that is very different from asking for a standard.
Yes.
So
yes.
people are running around to standard committees and standard bodies, but this is not what the European Commission at least had in there. The idea really is that the standards go by natural adoption. Of course, you can work on it if you like this, but you cannot dictate this from above. But this is what people do. Yeah, they deposit 500 standards, and then you have a complex situation where nobody knows what to do anymore. So I think the approach here, I mean, the question is rather, I mean, the standardized way of, like, the original question is, do we need a TNO? For me, that makes sense. Yeah, that is a standardized way of documenting your knowledge. And then whether the final system will be adopted by the industry, we have to work hard on that, but it goes via the industry and not via the standardization bodies.
Yeah, I agree with what Anne said. For example, we are working now on verification and validation, and we started to analyze which standards are covering this concept, and it's quite messy because there are different standards, everyone with his own interpretation, and it's really difficult to adhere to one, and so we are forced to create another interpretation that of verification and validation that tries to comprise most of them, but maybe this is not the right direction. So in my mind, there are two different standards: a de facto standard and a non-de facto standard. De facto standard are, for example, the International System of Quantity, or, for example, the vocabulary of metrology. These are de facto standards. Or, for example, the CIF dictionary for crystallography. So they are very narrowed and very well accepted. Then these are standards that can be that you can also impose. For example, you impose to users, and you can work on that and trying to express ontologically, say, oh, there is only this perspective. But in most of other cases, standards are non-de facto standards, so are simple formalized way to a formalization of some methodologies to deal with that domain. And I think that these for this non-de facto standard, for this plurality standard, I think that ontologies may be very useful, especially the onto-commons approach, in which we try to formalize, to conceptualize the standards and try to place them in the same framework by aligning them in a different way with some top or mid-level for mid-level framework, and then leave Darwin to do his job, which means that maybe some de facto standard will arise, or maybe in the end there will be a coexistence of few standards and so on. But one of the big problems that we have is that existing standards create a sort of confusion about what is the right definition of a concept. This holds not only for verification and validation, but also for product, which is a very important concept that has been defined in a different ways in different standards.
I just added something in the chat, so I didn't want to interrupt. And so I appreciate that. Anne said at the beginning, you know, I remember them telling me how the standardization process goes, and whoever's using it then should it should be plain sailing from then. So if now we've got 22 demonstrators in Onto Commons, okay, and you know, if we look at them and we're mapping the organizations mapping the standardization bodies, excuse me, who are part of these different demonstrators. Now, surely, you know, one of the aims is to demonstrate the effectiveness of OCUS, but secondly, surely we want to make sure that the demonstrator users are banging on the SDO doors saying, here is what I need, this is how this is going to work. And that's an effective proof of delivery that then is a standardized terminology that can go forward. I think, you know, isn't that what our ultimate aim wants to be? And it's good that Onto Commons has these demonstrators that do this. I don't know if we have our work package 5. Anyone on the call here that can add anything about the demonstrators, but I'm holding out for them as being the solution here from an Onto Commons perspective.
Well, to answer, I mean, your standardized terminology, then I certainly support that. We have in the modeling area deposited the CWA, because that's the form the ISO standard works. Yeah, if you talk about the terminology, then it is a workshop agreement. And we have deposited this, so that is a standard and it works. Yeah, it does work that you have made this public and that people have access to it. Of course, it doesn't mean that everybody agrees with the definitions, and some people will fight them until eternity and will not adopt it. But it helps that you have done this. And I think definitely if you can do this via the demonstrators and also find the terminology for those areas, then that would be a big step forward. And I think we can do this also in the domain ontologies, where you also can talk about the terminology as a first step towards an ontology. Yeah? You definitely first have to agree on the concepts that you want to put into your ontology. And this is the way that you can harvest the information. So there the demonstrators certainly will play a role. But I'm not sure whether your demonstrators cover the whole world that the NMVP program is supposed to cover. But that, I mean, you cannot reach completeness in a project of 4 years. Yeah. So you have to start somewhere.
Yeah, it's also, I mean, to initiate, I absolutely agree that we need to, you know, kind of initiate further such terminology work for sure, because also as we're already doing that in these so-called bridge concepts. So I showed, you know, the atom and the field, physical field, and so on. These are really detailed. I mean, we need this level of detail. And we have a great template now, I think, from the Onto Commons project to do that. But here we do maybe 5-10 terms, right? To do any sort of work like that requires enormous resources. As we also had in the previous talk, you know, it should really have also an industrial sponsor. There should be a serious time commitment to do this type of work. And I can tell the story of years of work leading to one CWA. I mean, I mean, almost immeasurable amount of
It was about 4 years for 40 terms, I think, in total, and it took me 15,000 email.
So this is the task we're faced with. Yeah.
But there again, I mean, if you then talk about the domain level, that you can also do only some 10 bridge concepts, this then also is an advocate of structuring your work in a top level and what is the mid level and then a domain level. And of course, the art is then in identifying which terms are actually important for a wide set of subfields. But to structure it this way is, for me, a very, very structured way of approaching this. So I think the original question was, do we need a TLO? And I think, yes, we do, because of this item. Yeah, material is a word that everybody uses, product also, yeah, structure also. And therefore, we should address those concepts first and see what the different ontologies do with it. Yeah. And then only, yeah, even in this project, you will never reach the application level. Yeah, maybe in the demonstrators, but structurally, I think that is not where you will be able to go. And therefore, starting with the top level is very, very smart. Yeah.
Maybe I will raise maybe some provocative questions. So, what is the?
Comment on something?
Please. Sorry, there is some comments here from.
Coming from an academia industry perspective, where I work with standards on a day-to-day basis, I am seconded to the BSI, and I look at the resources, and from morning what was said is absolutely true to get through the amount of resources. Just echoing that. But the question about whether we want to go into the standards perspective, because adoption is going to be key. If you look at material standards, I work to DIN standards, to ASTM, to A standards, to a variety of things, depending upon my knowledge of how I would like to do a particular activity. So, for example, if I'm working on some composites, for example, and I wanted to look at their structural integrity or any of those things, I'm just going to refer to a standard rather than me creating something. And the knowledge there is that I am using all of my fundamental physics theories, which is not what the standard is telling us, but it actually implies it. So when you're looking at this level of materials perspective and joining, I am not very sure if we have actually mapped onto exactly, because there is this debate about how do you look at the nomenclature of those terminologies. So which means has that mapping been accurate enough? Because if I have to say that, then I have to go back to Socrates. Okay, if I have to go to that level to pick up those terms and how it has evolved the thing. In my perspective, that may not be sensible. We don't have that resources to go back and do it. But perhaps if you look at the 303, where we were discussing, we are specifically looking at automation. And that is of interest for me. And how do I progress? And that's where earlier I had a question and I said, have you looked at how do we relate this with the material properties? Just the relevant information to help provide our end practitioner to go along and see, okay, that is the new remaining useful life because my material is degraded by X, and there's a causality there. Okay, so I'm trying to understand how do we then tell the industry, because if I go and say as an academic, hey, this is what you need to do, they'll come back and say, yeah, amazing concept. But if I say this is the standard, now the question to the panel would be, would you want to go through that entire standardization process? Because for me, a standard is the lowest common denominator that stands by itself and can be adopted across the industry. Okay? Or are we going to say, as a group collectively, perhaps we don't have to go through a specific standard level, but maybe release something called a specification, a publicly available specification, which again takes a lot of resources. It's halfway through your standardization process, and then perhaps evaluate it. Having these 21 odd things, fantastic. Gives you a lot of knowledge, a lot of information. But the question then goes back to, is us as gatekeepers, how do we look at translating this? Because tomorrow the industry would say, hey, there's another standard. And I'll also give you an example. I'm currently working on through life engineering services as a specification, trying to see the next stage of standard. It is kind of overlinks the asset management standard, which was probably, what, 8-9 years now when it's released. And it's taken almost a decade for industries to adapt it. Now, if I go back to the industry and say, hey, there's another through life engineering services standard you need today, they'll be like, oh my God, I've just rematriculated everything to attach to the standard. So I think we need to have that vision as a collective. At least that's my perspective in how I see it. But it'll be good to see what the panel looks at in terms of having these challenges. Do we know concretely as a team what are the challenges? I don't know if that
Did you
was
hear that
clear.
online?
Yes.
Partly, almost, yeah, all of it, not.
I don't know if Anne wants to say anything. So go on, Norman. My point is in the chat. Please go ahead, Norman.
The idea of a publicly available specification is one of the hierarchy of documents that can be produced by standards. The aim really of a standard, an ISO standard, is a world consensus. You want to have agreement that several people think this is a good idea, and is worth, or it ought to be worth considering, because several people have worked on it. They put a great deal of effort into it. They've put a lot of intellectual property into it. It should be worth considering just from that point of view. Whether it then becomes something authenticated with a number and a revision procedure and all the rest of it is partly administrative. The most important thing is to have the consensus. And these are all new, these ontology concepts are quite new. And we've had enormous problems in getting our information model approach accepted. We've spent 20 years trying to get the materials industry to understand that the material information could be digitized in a quite simplified way and can make considerable benefits. We've been totally ignored by everybody. So there is a real problem to try to get these concepts widely established, because there isn't the deep depth of understanding of what computer software actually works and how it has to operate. So I have sympathy with trying to get these ideas across, but they're necessary. They have to be, find a way to get them across. But somehow standardization sometimes put people off. They say, oh, well, it's making this bit, or it's not considered this bit, or I want something slightly different. So we need some kind of common understanding across the board approach before we move to some kind of standardization, formalized representation at international level. We need to find some way to get these concepts established. Maybe these demonstrators that's in Paula described are really, really important. We've not been able to achieve a similar kind of approach with the information models that we created. We've had them totally ignored. And so really uphill kind of battle to get these concepts established.
I
We
just
need
like
to find a way to do that, and I don't know what it is.
Yeah, I would just like to sort of add to that, or start there exactly what you said about the information model. So one thing is, I mean, because this is a session also about top-level ontology. So it's a question of, what does the ontology have to offer here, right? From this session's perspective, right? So the first thing is, I think we had also on the slide, it's not just an information model. It's not just a data model of the standard, right? So what we're looking is to project our knowledge here via the ontology. That means project the knowledge of that is encapsulated in the standard in the ontological form, plus ensuring that it fulfills all of the criteria of the merio-causality, that it actually is aligned with our fundamental understanding of science, right? That gives us an extra level of integration and interoperability when it then comes to someone else saying, okay, I've got another standard, right? At least we've got now another toolbox to say, okay, how does that fit within our general understanding system? That is for the people that work on the fundamental level. That's not to say that the engineer will have to do this. No, the contrary is that you can then build systems that are based on that, where you can say, okay, now I can integrate these different standards within one more fundamental system, top-level system, and see how this conceptualization, that conceptualization can be captured within that system. So when your situation comes, or now comes someone with another standard, I can start, at least that's my, hope and vision. I'm not saying that we've done it, to offer something which is more interoperable, more continuous, rather than, oh, yet another standard. Yeah.
I have a comment. In my opinion, you speak a lot about the science representation, which is true, but very often for the industry aspect, materials are done with processes.
Yes.
And it's an action. And maybe a part of adoption would be to clarify the link between the object and the action of producing it or using it.
Absolutely. So maybe I should also, not to be misunderstood. So this is not just about science in the sense of physics and so on. It's also more fundamental about, as we have seen in the different perspectives and so on. So it should absolutely deal with the questions of validation, verification. So how is that represented? How is processing and actions and so on represented? Can we have a fundamental agreement on these different ways of looking at things, so that we have, well, this is the top level proposal, right? That we have an integrative framework for different perspectives and different standards and so on. So it's not going straight from the standard to an information model, but from the standard via a real ontological view of the world to implementations that are then built on that. But it's a more of a vision than a reality.
So top-level ontology is essential. We provide this harmonization or facilitate the unified representation.
Yeah, but they have to be. I mean, that's obviously our view. They have to. This is where the rubber hits the road. It's like they have to be tested, how well different top-level ontologies actually function in providing this type of interoperability.
So then my last question would be, should the ontology development strategies actually be changed in order to, or adopted in order to facilitate, for instance, the more unified representation of the knowledge that we have in the various domains, and facilitate the alignment with the various top-level ontologies that potentially could lead, this alignment could lead to the more standardized representation of information. So do you think also that the methodologies for ontology development should be adapted to facilitate this harmonization?
I leave that to in my way. I'm not a developer.
Yeah, in OntoCommons we are trying to build recommendations that well, an ecosystem that is going to host ontologies. So it's going to put down the requirements that that ontology should have in order for them to be interoperable. I would say that there are different aspects that should be considered and that has been formalized in the OntoCommons project. The first thing is that there are different levels for the ontologies to be interoperable. The first one is the syntactic level. So you need to have ontologies expressed in languages that are compatible. So the first things to do is to create frameworks for ecosystem for ontologies like the OntoCommons one that requires a specific set of languages for the ontologies representation, because tools are using these languages, and so that's the first thing. If you want two ontologies to be used or to be comparable, you need to speak the same language. For example, it can be OWL or some sort of OWL sublanguage, or it can be Keef, or can be first order logic, or whatever. And the second step is the step of choosing top-level ontology for the development of the lower-level ontologies. One top-level ontologist could provide you a conceptual silo in which all the ontologies created there are interoperable. So this is a really important point that OntoCommons is built upon. The fact that the role of top-level ontologies is well acknowledged, and it is suggested as a way to achieve interoperability within the specific conceptual framework. And then the third step that OntoCommons is trying to provide is the possibility, is the alignment between top-level ontologies that will facilitate the alignment of the overall silos of top-level ontologies together. So that's the idea. So we the OntoCommons ecosystem is built upon this this structure, and I think that we need to distinguish the level of interoperability that we want to achieve between ontologies when we talk about interoperability. That's it. That's my opinion.
Any further comments?
Just to comment on Silvana's comment, yeah, I think the previous presentation, the keynote by Eliza Kendall, I think was a great example of, I guess the OMG, like Fiverr working with the OMG, and then ensuring standards that way. I think that we should all learn from that. Yeah.
So I think for us, we have to go to lunch here, and if there are no comments or any, then I think potentially we could close the session. Okay.
Thank you.
Thank you so much.
Thank you very much, everyone. Have a good lunch. Take care. Thank you.
you.
Bye-bye.
Thank you.
Thank you. Bye.